Swayam Prabha. Digital India. Educated India.
Good morning. Good morning. Okay, so last week we have seen basically we have concentrated ourselves on the behavior, most of all, of single elements. And now we start tackling the concept that these single elements must be assembled and form a building, form a structure. We do know quite well how to design for vertical loads, for gravity loads, which can be dead loads or live loads. But we do also know that structures need also to be provided resistance versus lateral loads. And where do lateral loads come from? Wind, surely wind, okay? Then in several parts of Earth, also earthquake. But very simple. Imagine that your element, your vertical element, is not perfectly straight, but has a tolerance. This is a letter E, which is, for example, a certain percentage of its 8. Okay, it's not fully vertical, it's a little bit like this. And you have a vertical load P here. Well, because of equilibrium, let's see if we can. We know, oh no, I want blue. We know that we do have a vertical force here equal to P. But you see, those two forces are no longer aligned along the same line. They form a bending moment equal to P times E. And this bending moment is clockwise. So in order to equilibrate that, you need to provide your element the capacity to resist also a lateral load, which is equal to P times E over L. Generally, in precast structures, we assume this eccentricity, this unintentional eccentricity, to be equal to 2%. So we always design precast structures to resist at least a lateral load equal to 2% of the weights. And how this resistance is given? Well, we have to provide the structure with what we call a lateral load resisting system or a bracing. How can I go on? Or a bracing system. This is a picture I took some years ago in Venice. You see, huh? This is real. It's not AI. No. This is real. It's not artificial intelligence. So, actually, this was a temporary installation in Venice. Every other year, they hold this biennial art or architecture exhibit. And well, besides the area, the exhibit space, there is also, some installation throughout the city. And this was actually a bracing system in this house? Well, as a matter of fact, Venice house, because of the settlement of the soil, can suffer some misalignment. The funny thing is that in Italian, we call the arm braccio, which is the same word as bracing. Well, let's go. I think could be. Okay, so for example, let us imagine, we already showed this figure. Let us imagine that we have to provide our structure, our building, the capacity to resist wind loads. And wind loads are a pressure, a suction here, and here suction forces. As I said, the suction is because when wind comes, wind is basically a fluid, which is air in motion. And the current of air must make this path. So whereas here the flow currents hit directly the surface of the building, here you create some turbulence areas which actually creates this suction. Well, the same thing happens in airplanes. You have a wing. At the tip of the wings, you create a turbulence because there the airflow has a discontinuity. And also, the wing is shaped like this. Also here you create a turbulence. And as a matter of fact, if you see, the tip of the wings has some, like spikes, which are exactly to favor the detachment of the turbulence and bring it far away from the wing. And also at the edges of the wing, at the very tip of the wing, you have the winglets, which in airplanes from different brands, I would say, come in different shapes. These are just to detach, to favor the detachment of the turbulence from the tip of the wing. Otherwise, it will generate some contrary effect. But anyway, you can see here, these are examples of how we can provide a building, a structure, the resistance to lateral loads. We can use shear walls, which are here. We can provide shear walls like this. We can provide cores like this. And cores also, perform the function of, hosting the staircases, the elevator shafts, and so on. But one very important part of the lateral load resisting system are also the floor. The floors in a well-designed building for lateral load resisting capacity must behave as rigid diaphragm. So first of all, let's start considering a single wall, okay? Well, you can consider this wall as it's shown here. The wall is generally quite slender. This is the depth of the cross section, this is the width, and this is the height. You have it fixed at the bottom, at the foundation. And if you imagine that you have a single-story building, okay, you have a force on the top, which is due to the lateral forces. So how would you imagine you will calculate, you will consider, you will design your wall? Well, you could say, if I have an element which is fixed at the bottom and there's a force on the top, I can consider it as a cantilever. And I can say that it deforms in this way, and this displacement U is equal to the force divided by the stiffness that we indicate with K. Now, if you go back to your structural mechanics handbook, you also find that this displacement U is F. If this is capital H, H to the cube divided by 3EJ. And so in this case, the stiffness K is equal to 3EJ over H cube. Okay? But there is a but. Or better, the buts are two. One thing, and let's try to go back here. So you see, imagine that this is a single-story building, okay? The shear walls, they are connected in some way to the floor diaphragms. Otherwise, the diaphragms could not transmit the load. But the diaphragm moves horizontally in its plane. In order to have this cantilever behavior also implies a rotation here at the top. Rotation at the top means that your floor should do a movement like this. But this implies that all the elements of the system will go under tension and compression. Actually, this is very difficult to achieve because the elements, the columns, are very stiff in the axial direction. So the elements, the diaphragms, rather move horizontally and do not rotate. So rather than being a cantilever, your wall is rather like this. You have a fixed edge at the bottom and you have a constraint which can move at the top, but just sliding, which cannot rotate. Well, at least this is the symbol that we use in Italy. We call this constraint a skate. Okay. Rotationally, we call it skate, pattino. You can just slide and not rotate. Well, as a matter of fact, this scheme, if you have rotationally restrained at the top, is stiffer than the cantilever. And this is the reason for which this is the flexural stiffness here that I put. I put a C here, because actually the reality probably is in between these two schemes, closer to this one. So if it would be a cantilever, this number will be 3. If it's this one, that number is 12. So the first thing that we have to consider is that, well, we are, tend to idealize, to model, to design our shear walls as cantilevers, but consider that they have a restraint at the top, a rotational restraint. So their stiffness is not 3J over H cube, but tend to be closer to 12 EJ over H cube. The other thing is that, especially for low-rise buildings, but generally, consider the interstory space. Interstory, even a low-rise building, what could be, 4 meters high. These shear walls can be 2-3 meters in plan. So they are not exactly like beams. They are squat walls because they are 8 in their depth. They are of the same order of magnitude. So in this case, it's not only the flexural stiffness that we have to take into account, but it's also the shear stiffness. in slender beams, the shear stiffness is much higher than flexural stiffness. So the shear deformability we can neglect. But in this case, the two terms can become, if not comparable, at least the shear deformation, the shear deformability cannot be neglected anymore. So you have to sum up, and we will see what that sum means, to include also the shear stiffness, which is this one here, GA over H, with me, which is the shear factor for rectangular cross-section, is 5/6. I said we have to sum up, but what does sum up means? Actually, this element is 1. And its flexural stiffness and its shear stiffness are participating, are sharing the contribution, the resistance to the shear force. So if you imagine these like springs, okay, how are they collaborating according to a series mechanism or to a parallel mechanism? You know, spring models are always useful in structural mechanics. I said they are sharing the capacity to resist to shear. So is this a parallel mechanism or a series mechanism? If they share, it's parallel. If you have a series mechanism, all the springs stay in the same force, and you sum up the deformability. If it's parallel, the deformation is the same. Actually, here, the deformation of the wall is the same. But it's partly due to the shear mechanism and partly to the flexural mechanism. In a parallel, but you share proportionally to the stiffness, yeah. The same. Oh, flexural. Oh, yeah. Sorry, you're right. This is series system. Yeah, you're right. It's written here. You're right. We sum up them. And so, yeah, in parallel, you sum up. This is the combination of the, this is the combination of the stiffnesses. Now I have to. There is also another thing. This cross section has also a torsional stiffness. You know, but torsional stiffness, you see, torsional stiffness is this one. Is G times B cube H. Well, if you compare, if we go back, you know, the flexural stiffness is proportional to BH cube over 12. And the shear stiffness is proportional to BH. So compare it to the flexural stiffness, the torsion stiffness, if you compare them, they go with the ratio B over H to the square. Now imagine that H, the depth, is a couple of meters, 2-3 meters. And the thickness, generally, we say don't go below 20 centimeters. So if you have 20 centimeters over 2 meters, B over H is 1/10. To the square is 1/100. So we can neglect the own torsional stiffness of walls. It's another case if you have elements like this. The torsional stiffness here cannot be neglected. But in walls, you can neglect. But if you have a system like this, okay, imagine that you have a system like this, and imagine also that your force, as it happens, is applied here with an eccentricity E. Because you also, you know, there can be different reasons, but also we say that we always consider a tolerance which is equal to 5% of the side of the building. So this force here is equivalent to a force in the middle, F, and the torsion, which is equal to F over E, because if you consider a rigid system, you can always move the forces. And in a system like this, how do you resist torsion? Yeah, you were doing something with your hands. How do you resist torsion? you resist torsion with a, it's not very clear. Let's try to see another column. You resist torsion in this way. So you exploit the fact that you can have parallel shear walls, but they are not concentrated. They have a distance between them. You exploit this distance to provide them a torsion, to provide the wall system a torsion resistant capacity. And so this brings us to make another consideration. How many shear walls and in which direction should I provide to my building? Well, first of all, you find written as a principle in design codes that you must provide lateral load resisting capacity according to, imagine that your building in plan is a rectangle, or you can, put a rectangle circumscribing it. You have to provide a lateral load resisting system along both directions in the plan of the building. Because, wind comes whatever direction he wants. Earthquake, generally, when it comes, has three components. And in several cases, well, the vertical component in most of the cases is not very high, but there have been earthquakes recorded where also the vertical component was high. But in many times, the two components of the earthquake, they are absolutely comparable. So you have to provide the building a system which resists lateral load in both directions. Then for wind, you design as the wind comes separately, only from one direction at a time. So if you have a building like this, and you know that the wind can have either a direction fx or the direction fy, you design separately for fx and for fy. When we design for earthquake, we make the analysis separately. In this case, we denote the force with an E, which stands for earthquake. But then, after we have made the analysis, we pick up the effects of the earthquake in the X force, and we sum up to 30% of the effects of the earthquake in the Y direction. So with earthquake, you don't sum the forces, you sum the effects. But this is a clear difference that designing for wind and designing for earthquake. Wind, you keep it separate. Earthquake. But this brings us to another consideration. Well, you have to provide, as we said, the building, the system, a lateral load resisting system in two directions. So imagine that you have a wall in this direction, and imagine that you have a wall in this direction, okay? And these are both B and H, these are equal. If the force comes in this direction, we said Fy. Well, in principle, both the walls resist that force, or basically, the force acts on both of them in a different way, and there is stress. But this wall that we call 1, the reaction to the force Fy is with a stiffness that we can schematize like this. Whereas this wall is B cubed H by 12. So there is once more the ratio of the stiffness, which is like B over H or H over B. So actually, the contribution that walls parallel to the action, parallel to the force can provide is 2 orders of magnitude higher than the contribution that the walls orthogonal to the action can provide. So these allow us to make a simplification. And we say for the effects of the forces, we will see that for the effects of the torsion, it's not like that. For the effects of the force, we only consider the walls that are parallel to the force. It's not that the others do not participate, but simply, since their contribution to the stiffness in that direction is 2 orders of magnitude lower, we can neglect it. So this is a simplification, but, remember, and I will show you at the end an example, that this is only for the force effect. If you have torsion, this is no longer true. And there has been in the 70s in Italy a very famous example we call the Torso House, which was not designed correctly, was a 2-story building, ground floor and first floor. The earthquake was very severe. The Friuli earthquake in 1976 was very severe. But this house, you can imagine, was a 2-story house, but collapsed because of wrong design, because it was not considered that there was a strong torsional effect. But then, okay, we have to provide elements in both directions. And these elements restrain, as we said, the deformation only in the direction parallel to their axis of major stiffness. So you can imagine that they act like this constraint for the whole building. Okay? So if you just put one wall in one direction and one wall in the other, your system in the end will be labile, we say, because it can have still some movement. You know, restraining also the torsional deformation is important. So you can provide, or better, you have to provide lateral load resisting elements in such a way that the system is statically undeterminate. You know, statically undetermination is very important because you allow for redistribution. And well, when we think of redistribution, I will show you an example on Friday about this. But when we think of redistribution, we always think, okay, there is an element which has failed. And if one element has failed, we will have the other elements able to take on. But let's go back to the lecture of Professor Pillai when it was Friday, showed about corrosion. We have made a study, and I will show it to you on Friday, where we had a very simple building. It was actually a water treatment plant. So the building was a series of columns with these tanks on the top. And the building was in a very severe environment because it was close to the sea, in an urban area, and there was a steel factory nearby. So you have the chlorides, airborne chlorides from the sea. You have urban area close to the airport, so a lot of carbon dioxide, also because of the factory, and also aggressive fumes from the factory. So we hypothesized that some elements could experience some corrosion. And which were the elements experience corrosion? Well, we said the wind comes from here, so the first elements to corrode will be the ones windward, and then progressively. Well, we observed that as long as the corrosion starts progressing, the elements corroded, you know, gave back some of their initial shares of the moments of shear and so on to the other elements. Well, luckily, the system was very redundant because you have a lot of columns and there was also a small shear wall, so you could have that. But this is also something, you know, this is very interesting. And I think this is also, you know, some of you are going into research and so on. This is also an important topic that with research we have to start tackle. So let's merge together material science, degradation science, and structure. That corrosion model that we have seen, let's embed it into a structural design model and see what does it happen. We have the tool, it's not that difficult, but I think it's, as Professor Pillai was saying, in most of the cases nowadays we say, oh, for corrosion, just design concrete and put this cement, this water, and so on. No, quality is important. Cover design is important. We also studied in this fact how the permeability to chlorides change thing. In some cases, after 150 years, the corrosion did not, or better, the chlorides or the carbonation did not arrive at the front of the rainwater. So that kept the structure. And you can imagine that structure, a water treatment plant, in the case of earthquake, is a strategic infrastructure because you want clean water to be available. You don't want to pollute the sewage system, the water table, and so on. Otherwise, you already have an emergency to deal with. You don't want a health emergency to affect you. So this is the reason, among the other things, also one of the reasons for which we have to this one. Sorry, I just cancel here, and then I can go back to the previous slide. You mean this one? Yeah. Yeah. Because you see, if you apply the principle of solid mechanics, basically what you can say it's here. You can say that this system is equivalent to have a fixed point over here, but around that point the building can rotate. In this case, you have not, because these two elements meet here, these two elements meet here, and these two elements meet here. You have not what we call a center of virtual rotation, because there are 3 points, not all the 3 lines converge in the same system. So this second system is stable. This one is unstable because you allow a point, a center of rotation around which the building can have some kind of motion. Okay. So now let's try to imagine this. Okay. How do we distribute the force among these 3 elements here? Well, this is a stable system in a sense that you have 2 parallel ones. No one of them has a common center. How do you distribute the system? So imagine that you have a force which is applied where it's written there. So first of all, the first thing that you have to do when you have a system of walls, you have to calculate the gravity center of the inertias. Because actually the building will react around that point. And on the other hand, where the forces are applied, we have said for earthquake, we consider earthquake through a static equivalent effect. So these are inertia forces. There is the ground motion. The ground motion is transmitted to the structure, which modifies the, content of the. But it means that the floors have an acceleration. Okay, the mass multiplied by the acceleration in classical mechanics is a force. So this is the inertia force. Since it comes from the mass of the floor systems, well, it's applied in the center of the mass. And where is the center of the mass? Well, more or less is in the geometrical center. For example, in this case now, well, it's true that we have a floor system and the center of the mass is at the level of the floor. But also our centroid, our centroid is here in the navel, as we say. And now we are sitting, so it's quite low. We do not make a big error in saying that everything is at the level. So the force is in the center of the mass. The center of the mass is well, sorry, should be here. The center of mass is there. Whereas with this system where you see 2 different walls, your center of inertia is shifted towards the lowest and farther from the highest. It's the same rule of the lever arm. So you can have, and it's common, a system in which your center of mass, which is basically the geometrical center of your plan, is shifted with respect to the center of inertia. This is the main cause of the torsional effects in earthquake and wind loadings. So this is the reason for which in any code worldwide, you find, please try to keep your design as much as regular possible. Regular means provide well-distributed, reasonably symmetric lateral load resisting elements. Do not change their position from one floor to the other. Provide a regular plan. Do not put too many, protruding parts and so on. So it's just, you say, well, an architect comes and he says, no, because I want strange, then the fighting starts. But it's okay. This is the first way to guarantee a good behavior under earthquake. Then the rest is a matter of analysis, is a matter of detailing and so on. But this is something which comes beforehand. It's part of the conceptual design. So the building must be, as much as possible, regular, because this, governs a very good response under earthquake, but most of all, reduces the torsional effects. For example, you can have, well, these are just examples, and you can work out the math. You can have shear walls, arranged like this, and the force coming in any kind of way. Well, you can use a method which is similar to the Ritter method that we use to calculate the truss systems. So we write some moment equilibrium equation once at a time, and we write them in such a way that each time we eliminate one contribution. So for example, you see, if you write the moment equilibrium equation with respect to the points where these two walls meet, the force here and the force here, they disappear. So you have just the contribution of the force, in this case is this one, times the reaction force of wall one. When you write, let's change the color. When you write about this point, which is 1, 2, force in wall one and force in wall two, they disappear because they converge into that point. So you can, in a very simple way, work out the forces in the system. This is another example. You can have walls or even different parts of a wall. You can have a sea wall. A sea cross section provides already some torsional resistance because, as you can see, you have these forces, R3 and R2, that give you the lever arm contribution. But this is also a very interesting example to show you we have a force F. Which is applied in, let's say, y direction. Imagine that x and y in the plane are the usual things, okay? And we have one wall in the y direction and two walls in the x direction. So we have said the walls or the parts of the wall in the x direction, they do not participate in the resistance to a force in y. So the force equilibrium will only be guaranteed by this element here, R1 equal to F. But then you see, R1 equal to F, but F is here. So there is this distance here, D. So there is a torsion contribution. And how this torsion contribution is taken? Well, it's taken by these opposite forces in the other wall. So this is just to show you that even if for the force, the elements participate in the lateral load only when the force is parallel to their main stiffness axis, for torsional effects, all the elements participate. And this is something very important that we have to consider. So now let's try. You have some elaboration of the maths in the slides, but I will try to make it simple and work out by hands. But these are the hypotheses Yes, these are the hypotheses that we make. We have infinitely in-plane stiff floors. This is the first assumption. The floors must be infinitely stiff in their own plane. As I said, when we have cast-in-place concrete structures, reinforced concrete structures generally, well, you can even make it partially prefabricated. You come with pre-dal slabs, which are slabs with polystyrene blocks, and you complete by in situ casting. That one can be considered as infinitely stiff. We made an example. We had this pre-cast, pre-stressed double T element, and we assumed, if you go back to the exercise, we had a topping on top. Well, in that case, you can consider that, you know, if there is a topping, you have infinitely stiff action. And in some, not codes, but guidelines, you find that, for example, you need at least a 5 centimeter topping to guarantee infinite stiffness. In some other cases, this has to be checked. This has to be checked. The other thing that it's not detailed here, but the floor must be infinitely stiff in its own plane, but also must be effectively connected to all the elements which have to resist the lateral loads. Because otherwise, since we have said the force is the inertia force is applied to the floor, there is no way to transmit it. So this is important. Then the bracing system is perfectly fixed to the base. So this is another thing that we have to guarantee. You see, in all these assumptions, it's implicit the strong and fundamental role of the connections in precast structures. And then we have elements which have a constant inertia along the height of the building. Or if the inertia changes, it changes in the same way for all of them. So what does this mean? This means that you have always the same ratios between the inertias. And you can adopt a simplified method that even for a multi-story building, you can just limit yourself to one story and consider the slab with its elements and the force which pertains to that story. So now I want to, so we have said we can consider floor, okay? And let us put here some shear walls. You know, this is not an exact way of positioning them, but we can have some of them like this, okay? I am drawing them in different colors purposely, okay? Imagine that it's something like this, okay? So you can have either a force Fx or a force Fy here. And we call this element, well, this element is 1 in the direction x, so it's x1. This is x2. This is x3. This is y1. This is y2, and this is y3. So now, you see, I purposely draw this system so that they are not symmetric. So I wanted the center of the stiffnesses to be not in the center of mass, because the center of mass is where the two diagonals meet, and it's here, and you see that these forces are exactly applied in the center of mass. So we can say that the center of the stiffness is, well, probably for this case it's here, and for this case it's here. So the center of stiffness, which we can call K, should be something like this, whereas this is the center of gravity that we call G. Okay? So the walls in the x direction have stiffnesses that we call kxx I, and I can be 1, 2, 3, whatever. Whereas the walls in the y direction have stiffnesses that we call kyy We use two counters, two different counters. Okay? So let us now start designing for Fx force. If an X force comes, okay, and we have said that the floor is infinitely stiff in its own plane, what kind of motion do you expect? Well, you can expect a motion. Let's put it, no, this is. You can expect a motion centering us in the center of stiffness. You can expect a motion that we call with the Greek letter xi in this direction. But if the floor is infinitely stiff, what does this mean? It means that all the elements of the lateral load resisting system, they undergo the same displacement xi. So this is fundamental. You know, this is an assumption that we use as an inborn idea. A French philosopher of the Renaissance, Cartesius, said that we are born with inborn ideas. So the concept of circle is an inborn idea. For us structural engineers, it's inborn, the fact that, you know, diaphragms are rigid, but we hardly consider that some cases they be not. You know, this is a very strong assumption. But if all these walls, x1, x2, xi, xn, whatever it is, they undergo the same displacement xi, each one of them will take a force, which is its stiffness times the displacement. And the stiffness is calculated according to those models that we have shown at the beginning of the class. So this is the force. This is the force that you have in each of the shear wall, let's call them, in the x direction. You know, this also, you know, there are two fundamental structural mechanics assumptions here. One is compatibility of deformations. All the walls, because of the rigid diaphragm, they undergo the same displacement. The other one is a constitutive relationship. You correlate the force to the displacement through a stiffness. It's linear elastic. Okay. Then I will comment the linear elastic fact in a moment. You know, all structural mechanics problems are made of three ingredients: compatibility, constitutive relationship, and equilibrium. So we have said already that here we have compatibility. The compatibility is in the fact that all the elements have the same displacement xi. We have the constitutive relationship here. What we are missing? The equilibrium. And what the equilibrium states? Well, we have a force Fx, which is the external action. We have reaction forces in the walls. The equilibrium states that the external forces must be equilibrated by the sum of the forces in each and all the walls in that direction. So if we have n walls in X, it will be a sum from I going to 1 to n of F inside. Okay? But you can replace this here, and you have 1 kxxi times xi. And you see here xi is a quantity which does not depend on the sum. It's a common term. So you see the power of that assumption. You see in this mathematical possibility of handling very simple this, and you find that xi is equal to fx divided by the sum from a1 to n of kxxy. But as a matter of fact, this is a displacement. So when we use this is like using the stiffness method in the solution of hyperstatic phrase. The solution of our equations is a displacement, is a deformation. Now we have to make one step forward, because as engineers, we first look into the forces, then into the displacement. Well, but if we want to know the force in each wall, just pick up this xi and put it here. So just, pick up the xi that you have calculated from here and substitute it here. And what you get is the force in each element is equal to the total force kxxi divided by the sum I1 to n kxi. So this is rigorously mathematically derived. What we generally state as each shear wall takes a share of the force proportionally to its stiffness, but comes from this model. Which is a model which is based on the assumptions that we have seen before, and is based on compatibility, constitutive equations, and equilibrium. That is. It's very simple. Well, as I said, stating that the force is equal to a stiffness times a displacement is a linear elastic assumption. Hooke's law. He discovered the elasticity law, and he, annotated in his books, in his handbooks in Latin, and he said, ut tensio sic vis. Vis in Latin is the force. Tensio is the elongation. And he said the elongation goes as the force. So there is a proportionality ratio. But, we are continuing to say concrete cracks. Reinforced concrete is a material where we do want to exploit nonlinear behavior of the material. But most of all, when concrete cracks, you already are into some kind of, non-perfectly linear elastic. But we are allowed by the codes, at least for the analysis, to perform a linear elastic analysis. But what is the effect of cracking? The effect of cracking, what is that? The main effect of cracking in any element? The stiffness. The stiffness drops. So the stiffness is here. So, but before you make the analysis and design your walls, you don't know how the stiffness will drop because you have not designed it yet. So you cannot calculate how much your stiffness will drop because of cracking. So the codes tell us, well, in the analysis, you can consider the effect of cracking, and you assume this stiffness equal to 50% of the gross solid stiffness. So you still keep the linear elastic assumption, but because of cracking, you reduce the stiffness. Okay. Now, let us see. Well, let's go here, but I would like to. How can I copy? I want to copy this, but I don't know how to do. Now, what we have done before is that we have only considered the effect of the force. But as I said, the system, when it reacts to a system of lateral forces, does not react along the center of gravity, because the system is made, you have to imagine it, that the system is made of, discrete rigid masses. Have you seen those, there are these desk toys that are made with spheres connected. It's like that. So you can imagine a series of discrete masses which are virtually connected by the diaphragm. So what is the system doing is that it reacts around this point here. So this force Fx here, with respect to this point here, has an eccentricity, which is, well, it's Ey, because the force along the x direction has a lever arm along the y-axis. So there is also a torsion moment which is Fx times Ey. And what is the effect of this torsion? Well, the effect of this torsion moment, you see, pinning about this point here, is that your floor rigidly rotates along a vertical axis. So you can say that there is, there is a rigid rotation here of an angle phi. And what is the effect of the rigid rotation? Here it's a little bit complete, but let's pick up this wall, the X3. You see that the X3, with respect to the center of rotation, has that Cartesian distance. You connect the center of the wall with the center of rotation. And this distance has two components. One is y3 and the other one x3. These are the coordinates, okay? So the coordinates of the centers of each wall we denote with small x, xi, yi, and small y, or with xj and yj in the other case, because also in this case, you can have, which are the principles of the solid mechanics. That if you have a system of rigid bodies, and this system of rigid bodies has a common center of rotation, each rigid body undergoes a displacement orthogonal to the line connecting its center to the center of rotation. And how big is this displacement? Well, if this is the radius, R3, this one will be R3 times phi. Here, there is another important assumption that tomorrow we will see how to take partly away. Well, actually, you see, the point will make a trajectory which is a small segment of an arch, of a circle arc. But we are describing it as the chord of that arch. That assumption is the assumption of small displacements. And we can, actually say, okay, the arch is r phi. But if it's small, the arch and the chord coincide, and the sinus of the angle coincides with the angle, and we can say that the chord of that arch is r phi. But now, look at exactly at that displacement. You see, let's use two different colors. That this R3 displacement here has a component along this direction and has a component along this one. The component along the x direction is equal to phi times y3. And the component along the x is equal to, well, we have not put signs here, but you can imagine that the axes are centered in this point, but they go like this, x and y. So actually, this one will be minus phi x3. So because of the torsion, each wall, because the same will be for all the other walls, each wall will undergo a displacement which is equal to the rotation angle multiplied by the Cartesian distance between the center of the wall and the center of rotation. This displacement will have two components, one in x and one in y direction. Here we bring back our main assumption, and we say for walls in the x direction, the stiffness contribution that they provide for a displacement in y is negligible, whereas we only consider the displacement parallel to that. So in walls, in the x direction, which is the force which appears? The force which appears is kxxa times phi times ya. And in walls in the y direction, you will have forces kyy times phi times xj. So you will have basically a system of forces like this and like this. So you see, this will be like this. And in this case, it will be like this. Because they rotate, accompanying the rotation of the wall. There is already one thing that you see. If we go back to the previous page, well, we didn't draw the forces, but actually, what we expected was a system of forces like this. They are all, you see, each force is this one, but they have all the same sign. So they have the same sign of the force. This is due to the force, but because of the torsion, you see there are some walls which experience an additional contribution. They sum up, but for some other walls, it's exactly the opposite. So because of torsion, when the force comes in this way, this wall is overloaded, and these walls are partially unloaded. But then, well, we must not be so content because earthquake can also come in this direction. So when the earthquake comes in this direction, it's exactly the opposite. So we have always to consider this fact, considering the double direction of the force and summing them up with the modulus and not with the signs. But overall, all these forces, you see, they come in different directions. Why? Because actually, because of equilibrium, we already have guaranteed the equilibrium versus Fx. What we are now looking is Fx times the eccentricity. So we are now looking into torsion. So this set of forces must equilibrate the torsion. And how do they equilibrate the torsion? Well, you see, this force here has a lever arm with respect to this. So its torsion contribution will be once more times yi. And this force here has a lever arm with respect to this. So it's one more like this. And you have a plus here. So the sum of all these forces in I from 1 to m, n, sorry, and the sum of all these forces in J from 1 to m must equilibrate the external moment. So as we have done before, here you see we have two sums, but phi is a common factor to all of them, so you can bring it out and you can calculate phi, and phi turns out to be equal to Fx times y divided by the sum I from 1 to n kxi yi to the square plus the sum from 1 to m in j kyy j xj to the square. What we do have here, this is the torsion. And here at the bottom, we have a quantity which is the polar moment of the inertias. So we are picking up each inertia and we are multiplying it by the square of its distance from the center point. Because the motion that is happening is, you know, something that you look from the top and you see your system rotating. So what does it matter is the distance from each wall from the global center of inertia. So if this force here is, you know, phi y3 times kxx or phi yj yi, sorry, kxxy. This is the contribution of the force in each wall. Then put phi here, and you find that each wall takes a force due to torsion Fxi due to torsion T equal to the global moment Fx times y times its stiffness in its own direction times its lever arm with respect to the center of inertia divided by, allow me to call this quantity here Jt, you put it here, divided by the polar moment of the stiffnesses. Divided by the polar moment of the stiffness. This contribution of the force must be algebraically, according to what we have said, combined with the one that comes from the force equilibrium. Well, the same model you do apply to the case of a force Fy is exactly the same. So actually, this is a very simple model. It's based on the fundamentals of solid mechanics. And for example, well, it's very useful for, even a preliminary design. And this is the method that you apply also in masonry construction. In masonry structures, in masonry buildings, the issue is that there you have the walls, masonry walls. At the same time, they resist the gravity loads and the lateral loads. For gravity loads, you know how to calculate the floor slabs, they bring the force. But for gravity loads, you use exactly the same method. Exactly the same method. So this is a very powerful. Now, what I wanted to tell you is this. I said there was in Italy, in northern Italy, Italy is shaped more or less like a boot. You can say that it's something like this. Milano is more or less here. There is this region here. Here we have Slovenia. There is Austria here. There is Switzerland here, and there is France here. Well, in 1976, there was a strong earthquake in this region. And in a small town, there was a house which was a two-story house, very simple in plan. This bottom floor had a wall on this side and had 3 glass walls. Because actually at the ground floor, there was a car dealer. So there was a shop. He wanted the cars to be seen, and to be seen also, during the day, during the night, and so on. At the top floor, there was the office and the house of the owner of this shop. But if we look at the plan of the building, this was a shear wall. There were just 2 columns here. So let's try to make a very simple calculation. Let's say that this is 5 meters. Okay. And this is 0.25 meters, 25 centimeters. And let's say that these columns are 0.25 meters square. Okay? Earthquake force here, F. Where is the center of stiffness of this system? Well, you see, the wall has a stiffness which is 0.25 times 5 to the cube divided by 12. Each of the column has a stiffness which is 0.25 to the 4 divided by 12. So the stiffness of the wall is 5 by 0.25, which is 20. 5 by 0.25, which is 20 to the cube. 20 to the cube is 8,000. So the stiffness of the wall is 8,000 times the stiffness of each single column. So if we go back to this relationship here, and we can say, well, that the force, this is the wall, this is the column, the force in the wall is 8,000 by 8,002 times F, and the force in the column is F in each column divide 8,000 by 2 and 2. Yeah, I consider the stiffness of the column as a unit And so the stiffness of the wall can be expressed at proportion. Well, you see 8,000 divided by 8,002 is 1, and 1 divided by 8,002 is 1 10 to minus 4, more or less. So it's completely negligible. So the wall was designed to take the wall share of the force. But what did it happen? Well, it happened that when the earthquake came, this force here, imagine that this was 10 meters, has an eccentricity of 5 meters. But as a matter of fact, since the center of stiffness was more or less in the center of the wall, all the torsional effect went on the columns. So if you go back to this formula here, actually in this quantity, here the wall does not count, or well, it's here, it's in the green part, because the xj of the wall is 0, or it's so small that you can neglect it. So what you have is that you have an f times 5 meters divided by the polar moment of inertia, and the polar moment of inertia is the stiffness of the column that we have said is 1, but times what? Times 10 meters to the square times 2. And then you have to multiply by 1, which is the stiffness of the column, times its distance, which is 10 meters. And what does this is? How much is this? Well, 110 and 110 simplify. This 5 simplify with this is 2. So you have actually that because of the torsion, the columns take up each 1/4 of the force. And because of equilibrium, well, actually, here the force in the wall, you cannot calculate with the same formula because we are going to the limit where the center of stiffness is 0. But this actually is unloaded of the same quantity. So those columns actually, those 2 columns actually, it's not true that they were not taking almost anything. They were actually taking 1/4, each one 1/4 of the force. Well, what this resulted in? This resulted into a displacement demand that column was not designed for. That column was designed just for vertical loads. But then you ask or to undergo also a resistance to a shear force, to a moment. And as we have said, in earthquake, it's not only a matter of resistance. It's also a matter of deformation capacity, inelastic deformation, because you want that big amount of energy, which is the earthquake, to pass through the structure, to deform it, at least the column remains a little bit like this, but does not fall down. And we will see tomorrow how can we deal with, because this can bring to second order effects. That column was not designed at all for that demand. So this has remained. If you try to Google, I don't know whether you find, but probably you can find. It's called, in Italian, is torsio casa. Torsio means torsion, casa is house, and town is Gemona del Friuli. If you Google it, you can find this. It has remained as a, example of bad assumption. Bad assumption. Actually, that house really collapsed on itself. Because then, okay, when the columns, they undergo a drift that they cannot resist, they collapse, it lose support, and the house fell down. Okay, so this is, a very simple. Then in the slides, you have also a more, how to say, symbolic elaboration. But I think this way of going through is more intuitive. And it's a very simple model. Calculate the lateral force for each element of